Hello and welcome to this video on time travel and the theoretical prospects of time travel. Unless of course we're making this video in the future so our past self can publish it to create a paradox. If that is the case, welcome to this video on less than theoretical time travel. Be aware though, this video may involve maths, physics and paradoxes. Time travel, which is the concept of moving between different points in time, has fascinated scientists, philosophers and basically anybody with a slight imagination for a very long time. It's a staple of science fiction. Time travel is also a somewhat serious topic in theoretical physics. There's a framework for it grounded in Einstein's theory of relativity, quantum mechanics, and some other more advanced concepts. Let's have a look at what's going on and some of the, theoretical mechanisms for time travel, the scientific underpinnings, challenges, and philosophical implications. It's all founded on general relativity. Time travel primarily stems from Einstein's theory of general relativity, published in 1915, and describes gravity as a curvature of space-time caused by mass and energy. The space-time is a four-dimensional continuum combining three spatial dimensions and one temporal dimension. General relativity allows for the configurations of space-time that could theoretically permit time travel. Time dilation is one of the simplest forms of time travel into the future. It's a verified consequence of general relativity. Time dilation occurs when time passes at different rates for observers in different gravitational fields, all moving at different velocities. For example, a gravitational time dilation, which has clocks in a stronger gravitational field, ticks slower. Near a massive object, like say a black hole, time would progress more slowly relative to regions with weaker gravity. This has been observed, let's say, for those who are in space with a clock and those who are on the ground with clock. There is a slight difference in the measurement of time between the two devices. If you have an exact mechanical match for, say, something on the ground and something on the ISS, you'll find the ISS version does tick at a different rate and therefore time travels at a slower rate. And then we have velocity-based time dilation. As an object gets faster, and more specifically closer to the speed of light, the time for that object slows down relative to a stationary observer. This is famously illustrated in the twin paradox, where a twin traveling near light speed ages less than a sibling on Earth. Time dilation has been experimentally confirmed. This is where we mentioned these atomic clocks. Atomic clocks are put on a fast-moving airplane or even a satellite in some cases, like a GPS system. What they do is it ticks slightly slower than an identical clock on Earth's surface. While this will allow for forward time travel in a practical sense, it does not enable travel to the past. And this brings us to closed time-like curves, CTCs. This is a much more speculative mechanism for time travel, including to the past. It involves closed time-like curves, and these are paths through space-time that loop back on themselves. This allows an object to return to its own past. These arise in certain solutions to Einstein's field equations. In 1949, Kurt Gödel found a solution to general relativity describing a rotating universe, where CTCs exist naturally. This is also called Gödel's universe. In such a universe, an object could travel along a specific trajectory and arrive at its starting point in both space and time. However, our universe does not appear to rotate in the manner Gödel described in a Gödel universe, although we presume Futurama does, given that Fry is his own grandfather, which creates that sort of paradox. It's actually an interesting explanation as to what's going on there.
Aw, I know how you feel. My grandfather died recently.
It's all so sad. At times like this, I just need someone to hold me. You like holding me, don't you?
Hey, you know what always cheers you up? Baking me a nice tray of sugar cookies.
How about these cookies, sugar?
Yeah. I shouldn't be here. I shouldn't even exist. But I do exist, which proves you can't really be my grandma.
Oh my God!
Huh? What the hell have you done, Fry? Relax. She can't be my grandmother. I figured it all out. Of course she's your grandmother, you perverted dope. Look!
Come back to bed, dearie.
Ah! It's impossible. I mean, if she's my grandmother, who's my grandfather? Isn't it obvious? You are. Ah! Ah! Ah!
Then we have wormholes. These are proposed by physicists like Kip Thorne, wherein wormholes are hypothetical tunnels connecting distant points in space-time. If one mouth of a wormhole is moved at relativistic speeds, or placed in a strong gravitational field, time dilation could cause a time difference between the mouths, potentially allowing for travel to the past or future. However, wormholes require exotic matter with negative energy density to remain stable, a substance not yet observed in the real world, so far less likely to happen. Kerr black holes are rotating black holes described by Roy Kerr's solution to Einstein's equations, and these may contain CTCs within their inner event horizons. However, these regions are problematic due to the somewhat extreme, if not obviously extreme, gravitational effects and singularities. You might arrive in the past, but you'll arrive in the past as a small mote of substance that's been compressed to that size by virtue of the extreme gravity. Obviously, you're not going to have much effect on the past in that case. Quantum mechanics and time travel are another option. Quantum mechanics introduces additional perspectives on time travel, particularly through the lens of quantum gravity and the behavior of particles at subatomic scales. We have the Deutsch model physicist, David Deutsch, who's proposed a quantum mechanical model for time travel using CTCs. In his framework, quantum systems interacting with CTCs resolve the paradox, like the grandfather paradox where a time traveler kills their ancestor, and by ensuring consistent histories. Deutsch's model suggests that quantum superposition allows multiple timelines to coexist, preventing logical inconsistencies. This approach remains controversial as it requires a specific interpretation of quantum mechanics. The next option is something like quantum tunneling and retrocausality. Some quantum phenomena, like tunneling, suggest particles can behave in ways that challenge classical notions of time, retrocausality. This is where effects precede their causes and has been explored in quantum mechanics, but it does remain speculative for macroscopic time travel. These ideas are still theoretical and lack empirical support for practical time travel. And this brings us to the challenges and certainly paradoxes. Time travel to the past raises significant theoretical and philosophical challenges and particularly paradoxes. The most well-recognized and understood is the grandfather paradox. If a time traveler kills their grandfather before their parent is born, how can the traveler exist to perform the act? Solutions include self-consistency principles proposed by Igor Novikov, and this principle states that any action taken by a time traveler must be consistent with the history that allowed the journey. Thus, the traveler cannot kill their grandfather. And it does mean the whole idea of if you went back in time and killed Hitler, will World War II happen? Moot. Many worlds interpretation. In this case, the quantum mechanics framework, time travel creates a new timeline or parallel universe, avoiding paradox by separating the altered history from the original. For all intents and purposes, it's the Marvel multiverse theory, just less profitable and less bullshit at this point. And finally, causality violations. Time travel to the past could disrupt cause and effect relationships. This challenges the fundamental structure of physics. Some physicists argue that unknown mechanisms like quantum gravity might prevent CTCs from forming. Then we have the practical and technological barriers. Let's say that even if theoretically possible, time travel was feasible, it faces immense practical hurdles. The most immediate and obvious is going to be energy requirements. Creating or stabilizing wormholes or CTCs would require not only exotic matter, but energy far beyond current technological capabilities. For example, stabilizing a wormhole might need negative energy, which is only observed in tiny amounts in quantum effects, like the Casimir effect. And then we have stability of space-time structures. Wormholes and CTCs are mathematically possible, but may be unstable or collapse under physical conditions. And, well, there's a certain lack of empirical evidence. There is no experimental evidence for CT's wormholes or exotic matter existing, making time travel speculative, unless you count the crazy guy down the street who claims that he came from the future, despite living in a cardboard box under an underpass. But there are, of course, philosophical and ethical implications. Time travel raises rather serious questions about free will, determinism, and nature of reality. If the past can be altered, does free will exist? Are all actions predetermined by consistent histories? There are ethical concerns, which include the potential to disrupt historical events or create unintended consequences across timelines. For example, if you went back and tried to alter history, would Japan become a rising power as the Soviet Union collapsed? Red Alert explores this idea in much greater detail, and much more enjoyable detail. These issues, of course, remain speculative, but are critical to understanding the broader implications of time travel. The current scientific consensus holds that general relativity permits mathematical solutions involving time travel, but most physicists consider backward time travel highly speculative due to the lack of empirical evidence and the unresolved nature of paradoxes. Forward time travel via time dilation is a well-established and experimentally verified form of time travel. So theoretically, if you want to go to the future, you can. Ongoing research into quantum gravity and string theory may provide new insights, but practical time travel remains beyond our current understanding and technology. In conclusion, time travel, particularly to the past, is theoretically possible within the framework of general relativity, quantum mechanics, and through mechanisms like CTCs, wormholes, and time dilation. However, it's not really feasible. The challenges that prevent that are clear enough: paradoxes, energy requirements, and a lack of empirical evidence. It's completely speculative. Forward time travel via time dilation is a proven phenomena, and, well, that one we can actually do something about. But backward time travel remains a frontier of theoretical physics, and most theoretical physics is basically exploring a very fancy thought experiment with fancy mathematics, but no real use beyond that, until you develop a nuclear bomb, at which time it goes from being theoretical to practical. Or perhaps we should say nuclear. Still, the idea of traveling back in time remains a frontier of theoretical physics and requires advances in our understanding of space-time and quantum mechanics. Thank you for watching this video. If you found it interesting, consider liking, sharing, and subscribing. And please do post any comments, questions, or suggestions you have below.